And welcome back. Good to be back. Good to be Bayesian, isn't it? I should ask, how is your prior so you had a prior distribution of belief about what this class would be like. How is it updated as you've gone halfway through? No, I'm just kidding. I should ask that question, but I'm afraid on the fly that might not go well. So I'm just going to let you say, if you have comments or suggestions, please send them to me over email or however you'd like to. But I do know that we were interrupted with my travel schedule, and I'm hoping to get back on track now. So let's just keep going. Does anybody have any questions for me before we begin? Anything that we covered? Homework topics, project topics, anything that come up? Yeah. Mm-hmm. Yes, thank you for asking. I was actually should have mentioned that last time. I'm going to be grading that either today or over the weekend. I'm sorry. This is like catch up week for me. But yes, it will be within the next 24 hours to, let's say, 72 hours. There should be grades, and you should see that in icon. That work? Yes, you will need some of the results from the first homework to do the second homework. For instance, the R squared section of the homework sort of gets you to think of generated quantities, but you'll have to adapt what you had before with a loop, probably, or there may be other ways to do it. I'll let you try to figure that out. But my goal in that is sort of the previous homework was take my R code and see if you can get Stan to run with it. And it looks like most of you have. And then this homework is now, all right, take my R code and change some of it within Stan. So we're sort of progressively building up the level of difficulty. But that doesn't mean you're not welcome to come and ask questions of me or Vladimir. Office hours, we have lots of office hours between the two of us, but also email or other ways as well too. We could also find a time to talk if you can't make office hours. All right? All right. Thanks for the question. Other questions? This is my time to open my water. Cheers. This is my question asking tool. I'm not, I'm a college professor, which means I got trained by in teaching by basically saying, here's your class, good luck. They'll tell you how you did at the end of the year. So I've learned over the years that you need to pause when you ask questions. And that's what water comes into. It helps me pause. Or hydrate. Okay, let's get started. Last time, as I was going through lecture, I had this terrible feeling about what happened with the multimodality. So remember last time we had this crazy setup where I was trying to introduce CFA, and sure enough, we had results for the factor loadings and for the latent variables. It looked like they didn't converge, right? R hats of like 1.53, a mysteriously consistent number. Turns out that was because of this feature of the negative lambda times negative theta versus positive lambda times positive theta being the same number. And so Stan itself sort of causes what ends up happening again. And I had that plot last time of there's these two modes of a posterior distribution, and Stan sort of starts perfectly in the middle of the two, and it's sort of a random chance as to which side it goes to. But once you get to that side, it sort of stays there. So I went back to the slides and I put some different code in to try to keep this from happening again. This is sort of things I'm going to teach you anyway. I told you last time about starting the init function and starting the lambda parameters very positive. Well, it turns out that usually works in CFA, confirmatory factor analysis. And part of that rationale, at least why I believe it to be the case, is because we're working with a very well-behaved distribution called the normal distribution. So well-behaved, we just call it normal. Crazy, right? No other distribution is normal. Okay, never mind. Stat humor doesn't go well at 9:30 in the morning. Vladimir's at least laughing. Thanks, Vladimir. Appreciate that. Lingua, thank you also. So the normal distribution makes things a little bit well-behaved. But when we get into IRT, which we're going to get into in just a bit today, we'll see that may not be sufficient either. Turns out one of my advisees, one of the people I advise, is trying to figure out best practices for how to start stan. To me, it's not a stan issue. It's just an engineering issue, right? So we like to have random starting values for our parameters, but that may lead us to this bimodality issue. So the hack that I think is working the best, although the research is yet to be completed, is the following. Let me show you how to do this here. So last time I showed you, we start all of our lambda parameters very positive. This starts them, basically what the init function does is starts the random values, basically saying that our lambdas are normally distributed, but the mean is 10 and the standard deviation is 2. And the reality is that is trying to get them to be super positive because the bulk of them usually are. It's seldom the case where all of them are negative, right? So if a few of them are negative, but the bulk of them are positive, that will do two things. Number one, it'll start us in the right direction for lambda. But number two, theta will also be in the right direction. Because remember, lambda and theta are tied together because we never observe theta. So that's one part of it. And if you end up having positive lambdas, they stay positive. If you have negative lambdas, they will eventually move to negative as well too. It may take a little bit more time to get there. But this is one catch. The other catch that I put in is with the other part of the problematic equation. Remember, it's lambda times theta that's causing the problem. Well, we can also put starting values in for theta. And this is where I think my favorite way of doing this is to basically take theta and think about what it's supposed to represent. In a latent variable model, typically if we're looking at a psychological or cognitive assessment of some sort, we tend to think that the higher a person's raw score or sum of items is, should be correlated with theta being positive, right? Because we often use a sum score as a proxy for ability or the trait or whatever. So we're going to do that. We could use that to our advantage, right? So what I'm proposing, or what I basically am suggesting and asking you to follow along with, is that theta itself, to start it at the standardized sum score. So let's talk about that for a second, right? The sum of all the items for a person is the sum score, right? But the metric of a sum score is on the scale of the test itself, right? So our example here has 10 5-point items. Items. The scores on each item range from 1 to 5. So we know that our range of our sum score should be somewhere between 10 and 50. That's incongruous with the range of theta, right? Where we say the prior distribution of theta has a mean of 0, standard deviation of 1. So we can't just easily put in the sum score by itself, most likely because turns out in the normal distribution, that thing will be our first estimate of lambda, and it may cause to determine the exponent to become so big it's no longer calculable by the computer. So instead of that, what I'm saying is we standardize the sum score, right? We subtract the mean and we divide by the standard deviation. So that is basically the z-score of the sum score. And we know standard variables have a mean of 0, a standard deviation of 1, so that puts it more similar to where theta is, and that should get us started in the right way. So this is how I've done it. The sum scores are basically the row sum of each of the items, and then for each person's initial theta, I just take the z-score of it, right? Subtract the mean, divide by the standard deviation. And then, going back to this init function, you'll see here, I actually use a normal distribution, but I set the standard deviation to 0. Now, I could allow theta to have a small standard deviation as well, too, but I set it to 0 because theta itself, that proxy for the sum score, should be sufficient for us to get started, and we have enough randomness with all of our item parameters that it likely won't change anything. So what I'm trying to tell you here is that really to fix this bimodality problem in a consistent way, we really need to be setting both lambda and theta. And I didn't realize that until I had taught the last class. But when I do that, though, as you can see, all of my results now change and look really nice. Nice. They look converged, right? And then you can see this is what the lecture should have been when I started last time. I sort of tried to clean it up at the end. The ICC, you have your latent variables, distributions, and so forth. But this is really, and just thinking of the sum score again, this is our estimated EAP. The y-axis is our estimated EAP of theta, right? So for all 177 people, we have their posterior mean of what their score should be, the latent variable should be. And then you can see it's on the metric going from -1 to 3. The sum score is 10 to 50. So this is where you can see they're highly related. We don't want to give Stan the answer, but we actually don't know the answer. The sum score is not sufficient for the latent variable in this case. And so, like you see here, the same sum score could have quite a range of latent variable values. But what we're doing, what our goal in initializing is to make sure that Stan moves in toward the right mode, because the latent variable makes the mode difficult. By the way, this doesn't happen. I've never had to have this conversation in the other Bayesian methods I've used, and that's because their algorithms work a little bit differently. And technically, it's theoretically possible to have, a Metropolis algorithm go the same way, because we're talking about the same posterior, right? If we use JAGs versus we use Stan, I should make this point really clear. The posterior distributions are the same. The differences between the programs is just how they approach sampling, right? In Stan, we're using really, quote unquote, efficient proposal values that are based on shapes of the posterior distribution that it can calculate, basically calculus terms. In Metropolis Hastings, we just use a proposal density that doesn't move us toward the center of a distribution. So in JAGs, which uses a lot of Metropolis Hastings or Gibbs sampling, we don't often see this because it's not trying to move us toward one of the modes, and it just sort of moves in the right direction. But secondly, JAGs may also does a different value, does different things for starting values as well too. So between the two, it happens. So again, if you see this happening, know that this bimodality doesn't mean there's something wrong with the model. It means this is the nature of latent variable in Bayes. Okay? Any questions on any of this? Yes. Great question. Great question. I set it to be 0 here just to make it clear that theta is the metric that we're going to. So if you can think about it, let's take a look at this plot right here. When I set the standard deviation, so what the sum score really is, what the standardized sum score is basically the configuration you see on the x-axis, but the numbers have changed, right? So when I standardize it at the x-axis, the center point is 0, and you'll see a range that's similar that you see on the y-axis. I set it to be the standard deviation to be 0 because I wanted to start each person exactly at that point. If I allowed some standard deviation to that, my fear was, if I allowed some type of variance, my fear was that we may end up getting enough variation that causes some of the thetas to cause us to go toward the negative side. So my practice, if you will, I don't know that I have any more data than that, although the student I'm talking about should have a paper coming out in the next few months about this. My practice is saying the latent variable itself, let's pin it down a bit in terms of starting point, but all the other parameters being random should be enough to allow us to have enough variation for the chain to converge in different spots if need be. But this I set to 0 for the sum score just to make sure that theta was toward the correct mode. I hope that answers the question a little bit. Thank you. I want, like, the true algorithm builder in me wishes everything could be initialized at random to start. Because initializing at random, there may be cases, like not what you see here, but here, let me get to this thing right here. Take a look at this bimodality. This is the bad plot, right? This is when we didn't do this. There may be cases where this type of bimodality occurs naturally. Now, in the models that we're working with in our class, it's unlikely. There's some other statistical theory that talks about whether or not distributions have one mode or more than one mode. And there's this set of distributional families called the exponential family, where the models based on the exponential family will have one mode. So we know CFA actually falls under that. So we know CFA is likely to be really well behaved in the posterior. However, it's possible that we put prior distributions on our model that cause something like this, right? And if there's multimodality in the posterior, the only way we're going to find it is through starting random initial values, right? If we always start the same initial values, it's possible, but it's highly unlikely that we're not going to find a bimodality in the posterior. And it's important. If this truly is the state of the world, we need to see it, because that gives us caution about our results, right? So to me, having a 0 for the standard deviation like I have right here is a bit distasteful, right? It may not be ideal, but in our Bayesian sense, I believe that letting everything else be random will allow for the chance to still have a bimodal posterior if it truly is there. Now, I will say, again, thinking more on the theoretical side of this, I will tell you that putting normal priors on lambda and normal priors on theta will not result in a bimodal posterior distribution, right? We can analytically derive what that should be, so long up to the part where theta and lambda have the same sign, right? There'll be two modes, theta times lambda and negative theta times negative lambda. So, long story, long discussion, but more just talking about some of the logistics in Bayes. Does that help? Okay. I answer questions too long. I'm just trying to help. I feel like I need to help the world. All right. Other questions? Yes, Vladimir. Mm-hmm. Yes. 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 Yes, that's the thing. In Stan, you can think of the process. Now, I'm giving you a very superficial treatment of this. Like, you can, if you're into the Stan manual, if you're into Hamiltonian Monte Carlo and the no U-turn sampler, the nut sampler in Stan, you may give me the finer technical details. But let me give you the higher order idea. There's this to propose a parameter. Stan needs to basically calculate the curvature of the posterior based on its knowledge of the parameter space it has now, right? And so why it does that is it's trying to propose a parameter toward the direction of sort of ascent, right? So if you think about a posterior distribution, actually, let me do a drawing here. Just a moment. Should have set this up earlier. Sorry about that. You can do it, movie. All right. So if we have, let's just take this as our posterior distribution right here. And let's imagine your starting value is right here. Okay? What Stan will do is sort of calculate the direction of steepest ascent. Like this is the direction you want to go. Right? If you propose anything in that direction, it's likely to be rejected. Right? So you want to go in the direction of where the posterior is highest. And that's why Stan creates really efficient proposal values, is the Hamiltonian process, this sort of momentum parameter that it gets derived, relies upon derivatives of the posterior distribution itself, right? Of our model data likelihood at times our prior. With those in place, basically, Stan is saying, oh, wait a minute, I don't want to propose anything over here because the surface is flat and decreasing. But I see, basically I have this momentum that's going to try to go up this hill. And if I propose in this direction, this direction, then I know it's likely to have a good chance of being accepted, or to have our starting value move to a place that's more central in the posterior, which is really what we're trying to get it to do. So because of that, when Stan starts, and we have this double hump camel looking posterior right here, and we start dead in the middle, right? Right about where the likelihood is equally flat on either side, right? If X starts here, Stan's likely to move it over there. But if we start over here, it's likely to go on that side because that's where the steepest direction is compared to it. Does that make sense? Yeah, thank you. And all of this was unbeknownst to me when I started working with Stan. So, should have known better. That's okay. I had that thing, like Stan was, like when Stan came on the scene, people were really excited about it. People are still pretty excited about it. And honestly, Stan is actually quite well made, right? I really like Stan. It is very good. But sort of the pitfalls of Stan, this is one of them. The other pitfall with it is the reason why Stan does not allow you to have discrete parameters is because you cannot take a derivative. You cannot take a gradient vector based on it. So you cannot differentiate something that's a step function. So Stan just says, we'll solve that problem by not allowing them. You can't have discrete parameters. Forget it. That to me is a pitfall in Stan. Not that you have to invent a derivative of a discrete distribution to use it, but more you could have used a blend. I believe there's an R package called Nimble, Nimble MCMC, which combines Hamiltonian Monte Carlo and like Gibbs sampling or Metropolis. So it does a Metropolis algorithm for the non-continuous parameters, and it does a HMC Hamiltonian for the continuous parameters. But I haven't used that yet. Actually, one of our recent graduates, that was part of his dissertation. He sort of combined the both. He created an algorithm to do both. Alfonso Martinez. So, assistant professor at Fordham now. So there you have it. But it was it could be done, but it's not. I don't know why I'm going on this tangent. Anyway, I'll stop. Thanks. Vladimir, did that answer your question or over answer your question? All right. What I need anybody to do is in the chat, when I keep rambling on like that, you can do this, which stands for too much information, TMI, or you can do that one, wrap it up. Like, okay? I encourage you to make snarky comments like that. Like, I will not take it personally, and I could use the feedback. All right? All right. All right, should we get into IRT? Does anybody else have any questions on what I just presented here? Okay, I'll stop. What I will tell you and warn you is that as I opened up my slides today, so I fixed my slides last time after class, reposted them, but I had already compiled my lecture slides for the IRT section. And of course, you're not going to see the sum score of theta in these, but I'll fix these afterwards. I did confirm that things converge to one mode. So at least this lecture will be not as embarrassing as the last one. But I will say that you will go back to seeing just the factor loading or the discrimination parameter go positive. All right, so I say this is IRT, but really what this is in the generalized measurement model context, what we're doing is modeling data that are dichotomous. So each of our responses are two options. Yes, no, agree, disagree, correct, incorrect, you name it. The methods that we will use today fall under the heading item response theory or item factor analysis. So that's what we're going to do. Turns out most of what you did for CFA will apply today, but there's some fun other bits of pieces of IRT that I want to show you. Because when you put things in a Bayes context, the beautiful thing about those posterior distributions is the noise to it. And we can use that to talk about noise and many of the other features of IRT that we are accustomed to. Now, if you're not familiar with IRT, I'm going to have a little bit of that in the lecture today. But basically, we're going to learn how to estimate unidimensional latent variable models with dichotomous data, which are item factor analysis or item response theory models. We're going to show how to estimate different parameterizations of these. So they're item factor analysis, item response theory are highly related. They sort of are different branches of the same tree. Item factor analysis, more psychology driven back in the 1960s and 70s. Item response theory was much more educational measurement driven. Both are approaching the problem the same way. Largely, they've been differentiated by how it's been estimated. In item response theory, initially joint maximum likelihood or conditional maximum likelihood for Roche models, and then moved to marginal maximum likelihood in the 1980s. Whereas item factor analysis took a different approach, and they had used limited information, what we call now limited information methods. So basically, estimate a tetraquark correlation matrix of your dichotomous data, and then make some assumptions about what underlies those variables and the correlation itself, and do factor analysis on tetraquark correlations. Today, we're all likelihood based with all of this. So limited information, it's more of a loss function, not less of a likelihood function, but these are the context for Bayes puts them both in the same likelihood, so they're very similar. There's a whole lot of, interestingly, IRT is an interesting field because one of the selling points people talk about with IRT we don't see much in CFA, which is things like item characteristic curves, test characteristic curves. These and other what I call auxiliary statistics we can actually derive from Markov chains as well, and I'll show you that toward the end, and I'll show variations of this as we go. Now I'm going to take the data we've been using and do the worst thing possible to it. All right, so don't do this with your data. All right, don't be like, hey, Templin, or cite my website, or cite the slides. Don't be like, Templin, 2024 said you could dichotomize your data. Don't do it. Hey, long story short, 20 years ago, I submitted my first paper to Psychometrics, and the reviewer said to dichotomize my data. Anyway, so don't do this. Wait till the next lecture. The next lecture talks about how we do categorical data versions of our model. But I wanted to have a cohesive set of data to run through the class. So I dichotomized my data. Okay? Now remember, should you do this? Negative. Okay? Don't do this with your data. In fact, if you do this in your project data, we'll have to have a discussion. I don't want to threaten anything. Let's not threaten. I'll just say that no threat. I'll be disappointed. Please don't do this in your project data. The bigger theory, the bigger picture I have is, how do I want to say this? Like when you go to the grocery store and there's like I like to call it the hippie aisle. The natural foods and the stuff. That's how we want our data. We want our data to be like all natural, all clean, not clean. Well, we need clean data, but we want it to be, don't manipulate your data before doing the analysis, right? But that being said, we will. Now in history, I will say there have been times where we've had to manipulate data. I was just on a thesis committee for a student in Brazil, of all places, that was using a machine learning algorithm to estimate like IRT models, Dichotomous IRT models, and sure enough, none of those algorithms could allow for discrete data or would allow for multi-category data in the way that needed to be done for the type of model he was estimating. So he did this. He actually didn't. Actually, he tricked the algorithm. Pardon me. He built a series of. Anyway, point I'm trying to make is there are times when yes, you have to manipulate your data to fit it into the process that only works for certain things. But our goal is to build a process that works for the data in the way it should be. So don't do this. All right, enough with that. Wrap it up, Templin. Too much information. Okay. So if a person, let's just do it this way. I like this. The easier one is a 1. If you see a 1 in the data, that's a person who responded with an agree or strongly agree. So that's somewhat affirmative is a 1. And neutral or negative is a 0 is how I coded this, right? If you don't like that coding, good. That's why we don't mess with our data, right? Like as I'm saying this, reviewer brain right here, or editor brain is saying, why is neither part of 0? Shouldn't that be part of 1? Good question. This is why we should not do this to our data. But I put it there for the sake of demonstration. Okay. Let's talk about this. This is what it looks like. This is item 1. This is now we have basically a histogram. And this then gives us the proportion of people who have rated an item as somewhat affirmative, either agree or strongly agree, for each of these items, right? So 16% for item 1, that was the highest. Item, where is it? Item 8, I don't remember which one that was. The NAFTA superhighway, whatever that was, 0.034. So somewhere between 3.5% to 16 or 17% are saying somewhat agree or agree to each of the items. How we doing? Cool so far? All right. Turns out there is a distribution for dichotomous data called the Bernoulli distribution. The Bernoulli distribution is a beautiful distribution named after a dude named Bernoulli. Bernoulli, I believe, was into gambling, roulette. I had some, vices to them. A lot of statistics, by the way. I think I've said this before. I'll say it again. Come from, if you back when data science wasn't a thing and people used to not want to do statistics, we'd have to try to convince students to make it interesting. And so I'd be like, hey, do you like beer? Hey, Guinness, t-test. You like gambling? Hey, Bernoulli, Pascal. Lots of the stuff that showed up in early mathematics and probability theory. Bernoulli gave rise to a distribution. Basically, the idea is this. It's a one-trial version of a binomial. So if you know a binomial distribution, this is the number of successes out of the number of trials, right? This is a count type thing. In our case, for the Bernoulli, there's one trial, and there's either a 0 or a 1 for how many successes there are. So what we call about the sample space, or the support of the distribution, y exists on either 0 or 1 in its set. So when you see this notation, this is just y is within the set of 0 and 1, right? It cannot be a continuous number. This is not when you see curly braces like this, for those of you who aren't into math, the notation game, that means discrete numbers, right, in the set, unless otherwise noted, is compared to, if we have actual brackets, that means a continuous number that includes 0 or 1, and if you have parentheses, it's a continuous number that does not include 0 or 1, right? Something along those lines. So the probability mass function, this is the likelihood function, or the PDF, but we call it probability mass because it's discrete, right? It provides a histogram. I mentioned that in earlier classes. We basically say the probability that y takes either a 0 or a 1 is equal to pi, which is a probability, raised to y, times 1 minus pi raised to 1 minus y. So again, thinking about what that means, if y happened to be a 1, pi represents the probability of that. So pi is the probability a 1 appears. Alternatively, if y was observed to be 0, right, this gets raised to a power 0, becomes the number 1, and multiplies 1 minus pi, which is raised to the power of 1, right? So you just get 1 minus pi, or the complementary probability of the probability of 1. So overall, the distribution has one parameter, pi, and that's the probability that y equals 1. Turns out that is actually the expected value of the distribution. And why that's important is, remember, in our generalized latent variable construct, we are going to model a function of the expected value. Right? So what we want to do is place a statistical model with a latent variable on our data for this pi parameter right here. Similarly, the variance of this distribution is pi times 1 minus pi. So interestingly, in this distribution, if you know the mean, you also know the variance. And what you can see with this distribution is, for instance, the mean, the point of highest variance is where the mean is 0.5, right? The variance at that point is 0.5 times 1 minus 0.5, which equals 0.25, right? As this mean gets close to 1, this variance goes down to 0. Similarly, as the mean gets close to 0, the variance also goes down to 0, right? So Bernoulli with one parameter is really weird for most of what we think about with statistics, because the mean and the standard deviation are tied together, mean and the variance. All right, so there are a little bit more teaching didactic thing here, the difference between dichotomous and binary variables. Dichotomous variables are variables that take two values, right? Dichotomous is usually two, dichotomy, like two, right? Whereas binary variables specifically take two values and they are 0 and 1. Right? So not all dichotomous variables are binary, but all binary variables are dichotomous. And as you can imagine, with the Bernoulli distribution being coded where we're using the 0 and 1 to raise a constant, basically being raised as powers in the PDF, we need the Bernoulli distribution needs us to have binary variables. Otherwise, if we raise pi to the power of 2, it's going to work the same. It's not going to potentially sum to 0 or sum to 1 across the different values of the distribution. Right? So Bernoulli distributions are for binary variables, and if you have a case where you have maybe a 2 and a 7 or something like that, we just recode it. But we need it to be binary as it enters into the distribution. Cool? Cool. All right. So here comes the problem. If we're going to use a generalized linear model with the Bernoulli distribution, our mean, pi, ranges from 0 to 1. Right? We need the mean to be on the space negative infinity to positive infinity. And so what we need to do with that is provide a link function, right? So we need to take a function of the mean, in this case f of pi, to provide us that results in a number that spans the real number line from negative infinity to positive infinity. And it turns out the two most common choices for this are the logit, or log odds, right? So let's deconstruct that just a bit. The odds, turns out if you have a categorical variable, we want to talk about odds, in this case with two categories, the probability of an event occurring is pi, right? The odds of that event occurring are pi over 1 minus pi, right? And we can think of odds as, if you have a probability of 0.5, then the odds is 0.5 divided by 1 minus 0.5, or 1. That means equal odds. But if you have a probability of, let's say, 0.75 here, then 1 minus 0.75 is 0.25. And we would say 0.75 divided by 0.25 equals 3. So the way we would interpret that is it is 3 times more likely that the event occurs than it does not. Right? Odds are wonderful to work in health sciences, survival analysis, and so forth. They're just hard to think about when you're used to probability, though. But moreover, odds are insufficient because odds come from range from 0 to positive infinity, only positive numbers. So when we take the log, in this case the natural log of the odds, every number that goes between 0 and 1 becomes negative, and every number that goes between 1 and positive infinity stays positive, and exactly at 1 it's 0. So now we get that real number line that we're looking like. And I don't know about you, it always felt distasteful to me a bit, because the odds here, like I just said, everything from 1 to positive infinity becomes positive in the log odds. Okay, that's a big range, but everything between 0 and 1 becomes negative, and now they're supposed to be the same? What's that all about? It's all about infinity, right? There's an infinite number of values between 0 and 1, and there's an infinite number of values between 1 and positive infinity, and we can't really differentiate infinity in that sense. So it may seem a little weird, but it turns out that's how it all functions. Does that feel weird to you? Do you ever feel that way when you take the log odds that, hey, I'm only taking the 0 to 1 numbers and mapping all of those onto the negative side, whereas everything above 1 becomes positive? Are you kidding me? That seems asymmetric, but it works out. All right. I hope you don't mind my math humor. I'm trying my best to, waste time. I don't know, not wasting time. I am wasting time, but I'm not trying to. It just comes natural for me. The probit, the other link function you may see often is probit. Probit is the term we give to the normal ogive. If you've heard of two-parameter normal ogive model, which is Lord's model from 1950 in his dissertation monograph, that is where it comes from. Turns out this phi function is what's used, and that equals to the cumulative distribution the inverse cumulative distribution function for a normal distribution. Ugh, it's a mouthful. Think of it this way. The probit, if we were to draw this a little bit, now this is supposed to be a normal distribution. That's pretty normal. There we go. Right? And let's imagine you have a probability right here of, let's call this 0.25, right? The area under this part of the curve is 0.25. What the probit will do is convert that area to the z-score on a normal distribution such that there was 25% of the area under the curve beneath it. Anybody know what that z-score is here? You know what we can do? Watch this. I can tell you what that z-score is. Go to my handy-dandy R calculator here. There we go. Negative 0.67. Right? The Q-norm function will do that. So basically, in my slides, right here, that thing, z, is the number that you end up with, right? So the integral from negative infinity to negative 0.67 of a standard normal distribution, PDF, is 0.25. So probit's a little weirder. It takes a probability and it maps it on. It says that's the number that came from a cumulative distribution, right? And that cumulative distribution's number, the area under that curve at 0.67 is where that goes. How many of you I'm assuming you've seen both probit and logit before, or most of you have. If you haven't taken IRT, you may have not. That's why I'm going a little bit slower on this. I will say this, looking between the two, show of hands, how many of you like logit better? How many of you like probit better? Let's say, who likes logit? More hands. All right, I'm going to say more hands for logit. How about probit? I see no hands for probit. Fair. You want some stat trivia, though? How about this? In 1993, again, many, many years ago, there's a great paper by Albert and Chib talking about how to use Gibbs sampling to estimate IRT models when they're probit, because we can basically trick the algorithm to run with data that have been augmented to be truncated normal. It's a pretty cool trick, and it was super good. Like, you can think about like it, to me, is one of the most efficient ways of estimating our models today, 31 years later. So don't hate probit just yet, okay? Probit rocks for some things. Also, if you're an M+ or a Levon and you use the limited information, that's probit as well too. So don't hate on probit. But from a learning of psychometrics perspective, when things go normal, like a normal distribution, they're normal. It works easy. When you don't do normal, it's all messed up. And there's a whole history. Like, there's a paper in 2006 by Holmes and Held that sort of show how to use Gibbs sampling with the logit like you did with the probit, and it's doubly complex and not nearly as efficient. And then there's later work, 2011 paper, I can't remember the author Poulsen, somebody that showed that this could actually be implemented with something called a Poila gamma distribution. And then I had a former student who worked on that at Kansas. We did that in IRT in a psychometric paper. Works a little bit better, but honestly, probit for what we do with Gibbs sampling is primo. Still pretty good. So anyway, I can't believe I just defended probit. I use logit for everything also, but there. I'm just trying to play devil's advocate. Leave some space in your mind for allowing for probit, okay? All right, less common link function. Actually, that's what we really need. I would love, like, I'm teaching in person next semester, and if those of you who want to take my class, if you just show up with a probit or a logit hat, like which team you're on, we'll root for it like a sports team. Yeah, go logits. And on that note, maybe we should start a university and call our football team the Logits. Wouldn't that be something? Anyway. All right. Enough with the word salad. Let's keep moving. There are, though, you may believe in, because in IRT text we usually just talk about logit or probit, there are a whole bunch of other link functions out there, right? And looking at latent variable models from the generalized modeling perspective basically will free your mind from thinking we just need logit, we just need probit. For instance, there are link functions like the log-log link that looks like this, right? The log, negative log of pi, taken to the negative log of pi Why log log? Well, both of those logs together put us into the real number line. You can actually map it. The log of pi. Pi is a negative number, right? Or pi is a number between 0 and 1. The log of pi, therefore, must be negative. So the result of this is a positive number. And the negative log of that results in a number that goes on the whole real number line. That is the rationale. There's also the complementary log, which looks very much the same, but it's just slightly different on the other side as well too. Right? We seldom see these in latent variable models, but we could. In fact, each has a slightly different curve shape, and each can be used in different situations. For instance, if you have very, like our data right here, we probably could use on, we have very low probabilities of someone endorsing an item, like saying affirmative to an item. That shape may be more suited to one of these other link functions. But again, in standard software, good luck, you have to have them listed there. In Stan or in Bayesian software like JAGS, you can build them yourself. You can use any of these yourself. So you get in a situation where you need to have a different link function. Now, most of you may never be in that situation. But if you do, this could be it. Here we have. So the inverse link function is the opposite. So we define our latent variables in the scale of the link function, but sometimes we want to convert back to the scale of the data. Right? So when we do the link function, we're in logits or probits. That means like our item difficulty parameter or intercept parameter are in logits, or the slope, what we call discrimination in IRT or factor loading in CFA, is the number of the change in logits per change in unit of the latent variable, right? So that the unit of it is still on this logit or probit scale. Sometimes we call that the model scale. But sometimes we want to talk about the data scale itself, right? Probability is about data, logit is about model. So what we have is the inverse link function, right? So if we have a log odds link function, the inverse to that is e to whatever was the logit over 1 plus e to whatever was the logit. So you often see that in IRT more, right? Similarly, this you will occasionally see written as this or that, depending on which textbook you're in and how much people wanted to have space for it. But I prefer this one right here. This just looks like a logit to me. But just as a heads up, the others are equivalent. You can mathematically rearrange them and show that they are the same. How are we doing? Questions? Okay, moving on. So let's talk about latent variable models with Bernoulli distributions for observed variables. Now note, we're not changing the distribution of theta. It's still going to be normal. The only thing different about this is the distribution of our data. If you did want to change the distribution of theta to a Bernoulli distribution, we might call that a mixture model. We might call that a diagnostic or cognitive diagnosis model. But we're not doing that, in part because Bernoulli distribution is discrete. And if we're using Stan, can't have discrete variables. So can't do that easily in Stan. There are hacks to it, but they aren't easy. Okay. So what we need to do is take our latent variable model and define it on the logit itself. So we use the logit link function, and we're going to take what we called the linear predictor from confirmatory factor analysis. That was the term without error on the right-hand side of the equation, what I used to call the theory part in our introductory lecture. And basically we use that for each item, right? So here, for an item I and a person P, the logit of the probability of someone endorsing that item is equal to our factor model that we had before, or our linear predictor, right? I apologize for this. This is a markdown error here. I'll get that cleaned up the next time, but it just covers each of these. But this, by modeling it with this, by putting this model on the logit, it looks really familiar, right? I mean, if we didn't know any better, this basically could be y on this side, and we're back into factor analysis land. And this is why I like this approach to teaching latent variable models this way. It's because the core of the model itself, what I call the theory part, isn't changing. The data changed. But with that, we can describe things a little bit differently. We have to remember that in our model, we're defining it on logits, not on the data itself, not an identity link. So that means each of our parameters are described in the scale of logits in this case. And where I say logit, if you have a probit model here, you just replace what I'm saying with logit with probit. Okay? So here the mean is replaced by the probability, right? This is our mean for each person. The mean for observed variable, conditional on theta. I dropped the conditioning argument here. The intercept is mu, right? So the intercept, just like we said in factor analysis, is your expected... In factor analysis, we said this is the expected response when theta equals 0, right? For us, it's not the expected response anymore. It's the expected log odds of the probability of endorsing the item. We have to sort of add qualifiers to it because it's in logit scale, right? And if we wanted to know what probability that was, if we take mu and take e to the mu over 1 plus e to the mu, if we stick it in the inverse Ling function, we'll get that probability back. We could. But that's the difference between model scale, data scale. But mu is in logits. Similarly, what we called the factor loading before, which will now be called the discrimination parameter in IRT, again, I mentioned this just a few minutes ago, it represents the change in logit for a 1 unit increase, or change, 1 unit increase in theta. So as theta p goes up 1, this is how much the logit changes. And I'm being very careful about my words there. It's not always positive. Like in an IRT class, we often think of these as being positive, and most of the time for simple measurement models, they are. But we say change because otherwise, if this is how much the load, it may not be positive. Positive means it's always going up. That's not always the case. So, depending on your field, the model from the previous slide can either be called a 2-parameter logistic model with a slope-intercept parameterization, or an item factor model. The latter one is a lot shorter. A lot shorter words. Although, it's funny, the term item response theory, if you think about it, there's nothing specific about that to indicate we have Bernoulli data, right? In fact, it might be the quintessential, most general name of all time. If you have an item and someone gives you a response, it's the theory on how you analyze that response. Nothing about the item, nothing about the response. Item response theory, literally everything could be item response theory if you think about it, right? So item response theory wins the award for most general name of a field that could apply to anything, but really only applies to one thing. Item factor model, what the heck does that mean? Right? Because your factor model exists and you had items before, but you weren't... Anyway, so the names themselves are kind of ridiculous, and at some point you just start putting symbols down and you say, this is the model I'm building. But let me give you a little bit of the lineage. The 2-parameter logistic model, right here, the 2PL, is from educational measurement. You can find a reference to it in Birnbaum's chapter in the famous Lord and Novick book. Are you familiar with those of you in our program have heard of Lord and Novick before, certainly, right? It's like a really important book. Let me tell you how important it is. If you can find a first edition version of this, first printing version of this, it may go for thousands of dollars, like on the open market, like on eBay or whatever else. When I was in grad school, and I kid you not, I ended up needing a new car. My car was kind of getting old and falling apart, and I needed more space. My car would run, but I needed some more space. So anyway, I got a new car, and my then girlfriend's mother had a copy of this book. She was a bookseller, and she needed the car. And I literally traded my car for that book. I kid you not. Yes. So for those of you who want to know history of psychometrics, Lord and Novick's big. So, and here's your job. If you want to get in on the Lord and Novick train, what we've done, and I say we in the biz, if you will. Like us students, whenever a professor retires, you got to get to their office first and find Lord and Novick. That's the big deal, all right? If you find that, keep it in your house under lock and key. Do not give it away. I kid you not. All right? How many of you have a copy of Lord and Novick? No. Now here, I'm gonna do something I shouldn't. Let's see if we can find it on Amazon. This is gonna ruin it here. Lord and Novick, hardcover. You see, it's not in print clearly. This is $100, but this is the second edition, second printing. The first printing has a black cover, so just be mindful. All right, you want that one. Go find a professor who's going to retire. Get Lord and Novick. Anyway, that's where the Birnbaum chapter comes from. Okay, there. Okay, less glamorous than that. There was a great paper by Christofferson in 1975 that was factor analysis of dichotomous variables in Psychometrics. That's the item factor analysis start. There were a few papers before that, but to me, the Christofferson paper sort of puts it together in a nice way. So if you want to see sort of the history of this, but from there, those are the branches of the tree. I would also add that the two-parameter normal ogive, the probit version, was Fred Lord in 1950. That's where we attribute it to. But since I'm talking logits, I talk about Birnbaum here. Similarly, I would say that the logistic version of this, you could talk about Roche 1960 is also being influential in that as well too. So there's a lot of references I'm leaving out. But here's the differences, right? Our normal distribution model, this is our CFA model here. We had error that followed some type of normal distribution in it. Whereas now we don't have error. So there is no unique variance. Oh no. There's an error. This needs to be no psi squared right here. No, I cannot draw. Oh my goodness. All right. Never mind. I was trying to make a note to make this repaired. I'll try to have to remember it. Actually, give me 1 second. I hate my typos. I will fix that and repost. The unique variance, residual variance, this should be psi squared. There's not one in Bernoulli distribution. So does that mean there's no error whatsoever in our model because we don't have it there? No. Error, turns out, if you think about how error gets expressed in this model, once we form this probability, this linear predictor, if we were to convert this back to the probability scale, error would be the difference between what that expected probability was and the extreme, right? The closer we get to 0 or 1, or the closer we get to 0 with probability, there's less error. So for us, we can look at it. We can look at it that way. On the model scale, back here in logit land, we don't often put error there, but we could in logits because actually we've figured out that if we were to define error there, it would be there, but it would have a couple features to it. Number one, error would be not normally distributed. Right? It would be logistic distributed from a logistic distribution. And the variance for it would actually be constant. Constant up to a scaling parameter that we usually fix to be 1. And that actually goes with the number, you may have heard this in multi-level classes, pi squared over 3 is the variance. So we could actually list it there and show it there, but we hardly ever talk about it because it's not really a parameter to be estimated. It's fixed. So that's one difference. Another difference is the link function, right? In Bernoulli, we had to use a logit because the mean turned out to be a probability. So we had to convert it into the real number line. In CFA, this thing is the mean, right? We saw that. We put that in the model for the means and Stan. And we don't have to convert it because it's already on the real number line. So that is the mean. And then, so this is the identity link function in CFA, whereas the logit link right here is in Bernoulli. So when you think about that, again, when I talk about the model scale, that means the link transformed, this term right here. So in Bernoulli data, in our IRT model or IFA model, the model scale is different than the data scale. But in the CFA model, the data scale and the model scale are identical because there is really just an identity link. The scale is the same. Questions? All right, so this is our way of going from one to the other, right? Most commonly, we describe the probability of a correct response as being in this e to the logit over 1 plus e to the logit. I will note I'm not conditioning on theta here, right? Normally you see this as conditional on theta. And the reason for that is it's somewhat interesting what we condition on, what's given versus not. Theta, mu, and lambda are all random in a Bayesian sense because we give them prior distributions. So if anything, we should condition y on all three. But that's a lot to write. So I don't define that. I just leave it as is. My shorthand for it. We could do that. So the models are equivalent though, right? This probability is on the data scale, but the logit is on the model scale. So if we were to put this into a simultaneous equation approach or like a path analysis, it would look like this. We have 10 items. Each of them has a logit of their expected value. And each one has their own linear predictor, their own item-based model. And we go through the same steps. So it's not the same as factor analysis, but largely it is the same as factor analysis, right? It's not the same in that we have to use a link function that's not identity. It is the same in that the steps are equivalent, right? Specify the model, figure out the identification method. What's its mean? What's its standard deviation for the latent variable? Estimate the model. Check model fit. If it doesn't fit, start over again. That type of thing. Or throw your hands up and decide to go and do a different field. It's happened. All right. Specify the model. We've already done that. Next step. Specify the identification method for the latent variables. We initially will assume theta follows a standard normal distribution with a mean of 0, standard deviation of 1. This is the most common way you see it done in IRT classes. And that allows us to estimate freely all item parameters of the model. And by the way, this identification method that we talked about with standardized latent variable versus marker item applies not only in CFA, but also applies in this IRT framework as well. So let me talk a little bit about model data likelihood functions. I realize at this point I haven't given you a lot of the likelihood functions themselves, so I'm going to do a little bit more of the math today. The specification of the model that we talk about defines this model data likelihood function. And to demonstrate what we can do here is the following. If we were to want to figure out, for instance, if we build toward this, we think about it right now, we could come up with this crazy joint likelihood function across all items. And that's usually defined in a Bayes sense. But let's think about estimating, if we wanted to estimate, for instance, the loading or the discrimination for item 1, what would the model data likelihood look like for that? Well, for us, that's a little bit easier because the model data likelihood for one item is the Bernoulli distribution. That's the Bernoulli distribution there. This is the mean of the distribution. So that our model would show up where the mean is, right? We'd have to take the logit, right? Actually, in this case, it's as a probability. So we take the inverse logit and we plug in mu plus lambda times theta. And then this is taken as a product across all individuals because we assume individuals are independent of each other. So this forms the basis for our model data likelihood function itself. And just if I were to go a little bit further with this, often we don't do this. Remember, a Bernoulli distribution returns a probability. And if you multiply probabilities together, you get increasingly smaller numbers, right? So oftentimes that's intractable for a computer because there's only so much precision you have. So what we'll end up doing is taking a log of that probability, right, itself. So we want a log likelihood function. Log likelihood changes the y-axis, right, the height, but it doesn't change the location of the maximum. And so here, if we were to take a log of that distribution function from before, it would be the sum of all the logs, right? The log of this thing, remember, log of a product becomes a sum across the terms of the product. Right, so that's where that log is. And then if we substitute in our model-based, our data likelihood, and our inverse link function for our model for that pi parameter, we end up with this right here. So why I'm talking about that is if you have everybody's value of theta, and you have this item's value of mu, you can now talk about the likelihood of any lambda based on this function. So what I'm trying to do is think about what's going into the Bayesian process itself. So this is an example, right? This is the shape. This is the log likelihood for a value of lambda. So basically, I've plugged in a value of mu and I plugged in everybody's theta, and this tells us the shape of the log likelihood for lambda. And if we were doing a maximum likelihood exercise, we would find the value of lambda where the peak of this curve happened to be, right? Right there. So that's the model data likelihood for lambda, right? All the other items don't impact it, right? All the other priors don't impact it. The prior for lambda will do this, right? We could do the same thing for theta, right? For a given person, the model data likelihood now takes our model and it varies the item responses. Right? So if we basically look at person 1, we would basically say, hey, this person had 10 responses to my items. Each one of those has an IRT model. I want to figure out the likelihood of their theta, and I happen to know all of the lambdas and all of the mu's. This is the shape of the likelihood function for theta. This is for theta 2, actually. Now, it turns out this is where you can start to see some of the weirdness of IRT happening. Because if you look at person 1's data, this is a person who had zeros for every item, right? Basically said, absolutely not. There's no conspiracy in any of this, right? Did not endorse anything. Take a look at this log likelihood function. What do you notice? Where's the peak? We haven't seen it yet. In fact, what it looks like it's doing is it's sort of increasing. There may be an asymptote, but it's constantly increasing. So it turns out, in item response theory, we have another glitch, in that just the model data likelihood for a person's latent variable may not have a maximum. Right? So if we wanted to get a maximum likelihood estimate of theta, not a Bayesian, not a posterior, but a maximum likelihood, this person would be infinite. We wouldn't, a negative infinity. We wouldn't be able to figure out where the maximum is. And that happens. In item response theory, anybody who has a response pattern that's all zeros or that's all ones will have a likelihood that doesn't have a maximum to it. However, and I don't show slides for this, and we're running out of time, so I can do a little bit to this. Theta, if we put a prior distribution on it, a Bayesian sense, and we look at the posterior distribution for it, we will have a maximum. So Bayesian methods in item response theory have been used to provide maximums and minimums for thetas that may have an infinite likelihood itself, not have a maximum on the range of theta. So we've seen this in psychometrics since the 1980s or 70s, as a matter of fact. Right? Almost since people started doing IRT, we've had to put prior distributions on theta. That is one rationale for it. It does provide a maximum. All right, any questions on any of this here? Okay, next. How do we do this in Stan? Turns out, start with the model. I always like starting with model, remember? Because that defines all the parameters. So here's the model for each item. This looks very familiar to CFA. The Y, the item response itself, is distributed as, and turns out in Stan there's a function called Bernoulli logit. This is awesome. going to the Stan documentation, let me show you this function real quick. Functions reference. Hang on. Stan Bernoulli logit. Here it is. And get the version, the new one. Bernoulli logit basically takes the logit of anything in the term. So what do I mean by that? Anything in the parentheses. Oh, I'm messing this up. Let's go here. So what this is doing is modeling, taking the logit value and modeling it with the term inside. Right? It's basically putting what we have inside into the likelihood function where in place of the probability, but it's encasing it in an inverse logit link. So it really makes coding quick. All right? Basically, we take our CFA model that we had before. We used to have it as normal, and the term right here was the mean. Right? That was the mean of the normal distribution. We just stick that in the Bernoulli logit function. That's it. Now you have IRT. Not bad, right? Why am I taking so long? Well, I want to go through all the... There's some certain catches to it, right? You'll also note we don't have a psi parameter. We don't have a unique standard deviation anymore. But we knew that going in. So there's nothing that we could do with that. There is a catch, though, with this. For you to be able to use the Bernoulli logit, you have to define y as an integer. And that causes a bit of a problem. And I'll mention that to you now, but I'll repeat this early next week as well. Again, this is our set of parameters. Nothing has changed with parameters. Still a vector for theta, a vector for mu, a vector for lambda. I should note our prior distributions are all the same as well. Theta has a normal distribution, standard normal. Mu and lambda have multivariate normal, where I define the mean vector in the covariance matrix. The data block is the big part that's different. Oh my goodness, are you kidding me, Jonathan? I don't even know how I got back to the front there. Oh, Templin. All right, here we go. Here's the difference. Y has to be an integer. And of course, Stan makes that a little bit difficult. You cannot define a matrix of integers. You can only define an array. So you have to put the syntax array, and then you have to tell it the type of variable that shows up in an array. An array is a computer object that's like a matrix but has more than just rows and columns in it, potentially. Well, the other part that's wrong with array is that the leading index for it has to be basically the columns that we had before, the items in this case. So to loop over an array, you have to start by looping over the first index. So here, basically, we've taken y and transposed it. I'm going to start up with this when we get to next week. So I'm going to stop here for today. If you have questions, just hang around after I stop the class here. But that'll be it for me. Don't hesitate to reach out if you have any questions or comments about homework or anything we've talked about today. And if you do have questions about today, just hang out for just a few minutes. Thank you. Have a great weekend, great rest of your week, and hope to see you next week. Take care.